In this video, we're going to take a look at the calculation involved in the standardization of potassium permanganate with a solution of ammonium iron 2 sulfate. So I'm going to focus only on the calculations in this video. The theory you should be able to get from your book or from other online resources like the Folan's videos from the experiments. For this, I'm going to give all of the ammonium iron 2 sulfate pieces of information a green colour. So here's the formula for it, and it says it's used as a primary standard. It was prepared by dissolving 6.86 grams of a crystal in dilute sulfuric acid, and it was made up to a solution of 250 centimeters cubed with deionized water. This standard solution was then titrated in 25 centimeters cubed portions, to which more dilute sulfuric acid was added. For the potassium permanganate, then I'm going to highlight in purple. So potassium permanganate was what it was titrated against. That had an average of 17.5 centimeter cubed when it looked at the mean titer. I'm then going to also take a look at the ratio in which they're reacting. So for every 1 permanganate ion we need 5 irons to react with it to get the redox reaction to take place. So, first thing I'm going to do before I even go into the calculations is I'm going to for myself, I'm going to draw a little sketch of what's after happening. So I'm going to have the volumetric flask here, and that volumetric flask was 250 centimeters cubed, and in the 250 centimeters cubed, what we have is 6.86 grams of the ammonium iron 2 sulfate. So ammonium iron 2 sulfate. And all that this is doing, you don't have to draw this sketch. You're not going to win marks or lose marks if you have it or if you don't. It's for me. It's for me to see what's going on in the question and just give me time to digest it and make sure I'm not going to go wrong with the simple stuff of filling it in. So I'm then going to draw the conical flask, because that's what goes there. And what I know then is once I have the molarity of that, it gets put into here in 25 centimeter cube doses, or in measurements. Then we have the burette, and in the burette is our potassium permanganate. And in the burette, when we ran it, it was 17.5 centimeters cubed of the KMnO4. So that's the key pieces of information. We can now go back up and take a look at the first part of the calculation. So it says to calculate the concentration of the hydrated ammonium iron 2 sulfate. So what I need to do is get it in moles per litre. So I don't have any information about moles in this scenario. What I have is grams. So I have the mass. And the mass at present is 6.86 grams. How do I go from grams into moles then? What's the connection? The connection is to use molar mass. So I need to involve molar mass, and then I will see how to get out the moles. Do I multiply it or divide it? So let's take a look at the formula for it. So we have ammonium iron 2 sulfate. So this is what the formula is. So we're going to have to break that down for ourselves. So we have NH4 by 2. We had SO4. We had the Fe. We had the SO4 again. So just checking I got that right. NH4 by 2, SO4 by FeSO4 by 6 H2Os. So, and 6 H2Os. Okay. So, now I have to get the molar mass of this. So I'm going to write the formula and then I'm going to write molar mass. And, by the way, I should have labelled this as question 1. So be very clear as to what part of the question you're addressing when and where. Now, I'm going to get the atomic mass of each of these. So I'm going to have that nitrogen is going to have an atomic mass of 14. So I'm going to have 14 by 1. So 1 by 14 plus 4 by 1, which is for the hydrogen. all of that multiplied by 2, because I'm going to have 2 of those. I'm going to have SO4. So I'm going to have that twice. So I'm going to just help myself here, and I'm going to calculate that as 2 by SO4. So SO4, first of all, is going to be 1 by 32 plus 4 by 16. And then I close that bracket, and then I'm going to have iron, which is going to be 1 by 56, and then I'm going to have 6 by H2O, which is going to be 6 by 1 by 1, 2 by 1, so 2 by 1, and then I'm going to have 1 by 16. The next step then is to take our time totting all of that out, and I'll have to calculate that in my calculator. It's just too long, so if I do it in my calculator, I'll get 392 grams per mole. So I like to work with the units. It allows me to keep track of what's what, and also gives me a clue as to how to construct the next part of the calculation. So we said that we wanted the molar mass, and we wanted to involve that with this mass. So if I take a look, I have 6.86 grams, and I have molar mass here, which is the grams per mole. If I take a look at that, 392 grams per mole, and what I would like to have as my units is MOL, just the moles. I want that to be on top, and I want the grams to cancel out or drop out or to undo each other. So I want the grams here, which is multiplied, or 1 gram, and I want to then divide it by grams here to get rid of it. So I'm going to actually say multiply by this, changed around. In other words, it's that divided. But if you want to go straight to this step, if it makes more sense to you, you can. So 1 mole over 392 grams. And if I do that out in my calculator, then I'm going to have, let me see, so I'm going to have 6.86 divided by 392, and I'm going to get 0.0175. The grams have dropped out, and I'm just left with MOL. Let's go back up to the question and see have we answered it fully. So we go back up. It said calculate the concentration of it in moles per litre. So I'm not quite done yet. I needed to get the moles per litre. So that is the number of moles that we had in 250 centimetres cubed. And what I wanted to get was the moles per litre. So I'm going to have 0.0175 moles, and I'm going to change it to 250 centimetres cubed, also known as millilitres. What I know about millilitres is that I could also write it as by 10 to the minus 3 litres. And if I actually divide that in then, so if I divide 0.0175, if I divide it by 250 by 10 to the minus 3, I'm going to get out 0.07, which was moles per litre. Now, you might be thinking, oh, well, you could just multiply by 4. You absolutely can. I'm just showing you this skill as we might need it later on, where we change centimetres cubed into millilitres into litres, and then we divide it in. That's the first part of the question then, and that tells us, and I can add this to my diagram then, that this concentration was 0.07 moles per litre. But I didn't use a litre, I used 25 centimetres cubed, so we'll be back to that in a moment. So I've done the first part. Part 2 then was the number of moles of iron in the 25 centimetres cubed portion. Okay, so if I just take a look at this formula again for a minute. So where the confusion happens for people is that we've just seen that this is the full formula, and we've just measured out that it's 0.07 moles, which is how we count kind of how many molecules of this we have on a big scale, moles in 1 litre of this. And now all of a sudden they're switching it up, and they want us to talk about it in terms of the moles of iron. But if you have a look at the structure of the formula, right, and we zoom in on the iron part, for every 1 compound of this, or complex of this that we have, I've got one iron at the centre of it, and that iron is what's doing the reacting, what's doing the work. So it's a 1:1 ratio. I don't need to double it or anything like that. For every one of these compounds that I have in the solution, every one of these molecules that I have in the solution, I'm going to have one iron that's reacting. And that's what's doing the reaction as part of the titration. The rest of it isn't involved. So we're just looking at the iron part that's doing the reacting, and because it's one iron that's given to us for every one of these compounds, the number of moles of the ammonium iron 2 sulfate matches exactly the number of moles of iron. If this had a 2 down here, well, then I would double it. If it had a 3 down there, then I would triple it, because I have 2 irons for every one compound that I have. So I'd double it, or 3 if it was 3, and so on. So to get the moles of iron in 25 centimeters cubed, what I'm going to do is I'm going to say, right, I have 0.07 moles per 1 litre. I'm going to change this 250 centimeters cubed into 25 millilitres, and like I showed you a minute ago, change the milli into 10 to the minus 3 litres. Now what I can do, I want to get rid of the litres, so I'm going to multiply by 25 by 10 to the minus 3 litres. The litres will drop out and we'll just be left with moles. And if I do that out and I do my calculation out here, what do we get? So I'm going to have 0.07 times 25 by 10 to the minus 3. So I'm going to get 1.75 by 10 to the minus 3, and then I like to stick the units in at the end. You won't get docked marks for leaving them out, but it'll help me to keep track of what's going on in the question. So just a little sketch for myself. What I know now is in the conical flask, when the reaction happened, there was 1.75 by 10 to the minus 3 moles of iron. That's how many iron particles there were, or iron atoms there were. Remember, moles are just a way of counting massive groups of atoms. And the next one then, part 3. So I've done that. I've just answered the question for them. They wanted the moles of iron. So we go back up now and we look at the next part, part 3. The number of moles of potassium permanganate required to oxidize the quantity of iron. So that's where our ratio comes in. So we got the moles of iron. I'm now going to look at the ratio of iron to MnO4. So I'm actually going to go back up to look at the balanced equation, and it's telling me for every 5 irons that I have one of these. So I'm going to put 5 under iron, and I'm going to put 1 under the permanganate. And then what I'm going to do is I'm going to put this in. So I'm going to say 1.75 by 10 to the minus 3. That number is 5 times bigger than the number that should be over here. So what I'm going to do is I'm going to divide it by 5 to make it 5 times smaller. So 1.75 by 10 to the minus 3, divide that by 5, and I'm going to have 3.5 by 10 to the minus 4. And I'm just using the ratios there to deal with that. So it's looking at, right, 5:1. What's another way I could say 5:1? So think back to kind of equivalent fractions, if you can think back to that skill that you might have for maths. I have 5:1 there. I could also represent it as 5:1 in this way. Because I said, if this is 5 times bigger, well, divide that and I'll get this on this side. So that's how many moles of the permanganate that we have now at the end of the reaction. So we've done part 3 and we're looking at the next part now. So part 4, calculate the molarity in moles per litre. Okay, so we have information about the number of moles. So I'm going to calculate the molarity of the potassium permanganate. The number of moles that we have was 3.5 by 10 to the minus 4 moles. And then I need to know moles per litre. Okay, so that's where knowing your definitions is really important. Molarity means moles per litre. I didn't have a litre. That many moles came out of, if I go back up to my sketch here, it came out of 17.5 centimetres cubed. But remember my trick. I don't try to, do anything with multiplying. I try to keep it simple every time. So this is the number of moles in 17.5 centimetres cubed, which is equivalent to 17.5 millilitres, which is the same as 17.5, and you should be able to get at this stage, by 10 to the minus 3 litres. Okay, so that's what I have. I've got 3.5 by 10 to the minus 4 moles in or out of 17.5 by 10 to the minus 3 litres. And I'm going to do this out then. So I'm going to have 3.5 by 10 to the minus 4. I'm going to divide that by 17.5 by 10 to the minus 3. And what I get there is 0.02. And that is moles in 1 litre, or moles per litre, also known as the molarity, capital M. Okay. Now, that's the number of moles that we have. What we can do with this then is we're asked to do a second part of that, so a part B of that. So we've done the part A, the moles per litre. The next one is to do part B, the grams per litre. So we've already done the little bit of work on this already. We looked at how do you connect grams and moles, and we said it was molar mass. So what we have to do here then is we're going to first have to calculate the molar mass. So the molar mass of our potassium permanganate, so we're going to have KMnO4, and we're going to calculate the molar mass of that. So potassium is 39. So 39 plus Mn, which is going to be 55. So 55 plus 4 oxygens, which is going to be 16 by 4. And we're going to tot that up there then. So we're going to have 39 plus 55 plus 4 by 16. And when I tot that up, I get that the molar mass in grams per mole is 158 grams for every 1 mole that I have. I then look at the units. That's just my way of doing it. I look at the units and I look at what I have. So I'm going to have 0.02 capital M, which actually means moles per litre. And what I would like to do is get rid of the moles and introduce grams on top instead. So I'm actually not going to need to flip it or divide or do anything strange with it this time. It's exactly how I want it to be. If I multiply it as is, the moles will drop out, and I'll have grams on top and then the per litre. So I'm going to multiply that then, and I get 3.16 grams per litre. And that's it. So that's the calculation for the standardisation of the potassium permanganate. It's much the same for every one of the titrations that we will do. There are some minor differences when it comes to the iodine calculation, so have a look at those. But the calculations each time are going to be the same. So you find the number of moles of what's in the conical flask, so how many atoms are in there reacting, and we group the atoms into the moles. And then we see, okay, if there was that many moles of them, what was the ratio in which they reacted, and then how many moles in the number of centimetres cubed that you've added. And then we can change that into moles per litre. That part will be the same every time.